Welcome to my talk on the representation of correlated exponential distributions by phase-type distributions. My name is Peter Buchholz and I'm from the TU Dortmund in Germany. Let me begin with an outline of the talk. I would like to start with the representation of exponential distributions by phase-type distributions and in particular by acyclic phase-type distributions. We present or try to represent exponential distributions by phase-type distributions to describe correlations in stochastic models. So the next step is to show how correlation between acyclic phase-type distributions can be integrated. I would like to talk about optimal representations in a sense that we would like to have a representation with a small number of phases to represent a given coefficient of correlation. And finally, I present an application example from the queuing area. Acyclic phase-type distributions have the advantage that canonical representations exist for them, which is not the case for general phase-type distributions. We consider two possible canonical representations. The first describes a version where we have n input states and one output state, and the second describes a canonical representation with one input state and n output states. It is easy to transform one canonical representation into the other by simply reversing the rates. Details are given in the paper. To describe an exponential distribution by an acyclic phase-type distribution, the Laplace transforms have to coincide, and we assume here that we have an exponential distribution which is normalized, so the rate is 1. This is not a restriction because we can multiply the rates by a factor to obtain an arbitrary exponential distributions. Different quantities are used on the following slides. We start with a vector of sojourn times depending on the entry state, which is denoted as m, the vector of sojourn times depending on the exit state, a, pi, the entry probabilities, and psi, the exit probabilities. All quantities can be computed from the vector and matrix describing the acyclic phase-type distribution. We consider two different variants to combine phase-type distribution and to define correlated phase-type distributions. The first is a parallel composition. In this case, we combine two phase-type distributions in the first canonical form by defining joint initial probabilities. Pi 1, 1, for example, is the probability to start synchronously both phase-type distributions in state 1. And of course, we have n times n1 times n2 different probabilities which have to be defined here. And we have n1 plus n2 linear constraints which have to hold to keep the marginal distributions. The second possibility to combine phase-type distributions is the sequential composition. In this case, a phase-type distribution in the second canonical form is combined with a phase-type distribution in the first canonical form by redirecting the output from one state in the first phase-type distribution to a state in the second phase-type distribution. Psi 1, 1 is the probability of redirecting an output from the state 1 to an input of state 1. Again, we have n1 times n2 different probabilities, and we have n1 plus n2 linear constraints which have to hold to keep the marginal distributions. The resulting phase-type distributions are used in stochastic models, for example in queuing models, to describe correlation. And since these models are usually solved numerically, state space explosion plays an important role, and it is important to find representations with a small number of states to describe given coefficients of correlations. And this is the goal of the methods we present in this paper. If the phase-type distributions are given, the computations of the probabilities to obtain a minimal or maximal coefficient of correlation is simply a linear program. Shown on this slide for the sequential composition, a similar program exists for the parallel composition. More challenging is the question how to find representations of a given dimension to minimize or maximize the result of the linear program, or in other words, how to parameterize phase-type distributions to obtain vectors A and M that minimize or maximize the goal function of the linear program, and this is what we consider for the rest of this talk. A paper by Blood and Nielsen from 2010 exists where they define phase-type distributions representing exponential distributions for sequential composition, and in their case they choose the phase weight mu I equal to I. This results for the first canonical form in initial probabilities of 1 divided by n, and they show that if they combine two identical phase-type distributions sequentially, then the maximal coefficient of correlation for n phases is given here, and the minimal coefficient of correlation is given in the second equation. If we consider the limit of n going to infinity in both cases, the results are optimal, so we obtain a coefficient of correlation of 1 in the positive case and 1 minus pi square divided by 6 in the negative case. So the question is where can we try to improve the result, and the goal is to find representations here which need a smaller number of phases to obtain the same coefficient of correlation. We were indeed successful for the case of positive correlation by using a stepwise approach where we add phases consecutively. We start with an exponential distribution and then add phases where the rates are computed according to the equation shown on the slide. This approach shows the faster convergence towards coefficient of correlation 1 than weights equal to I, and additionally the local conditions for optimality are observed, so we have at least a local optimum in this case. It is probably a global optimum, but this has not been proved completely yet. If we compare the convergence towards the coefficient of correlation equal to 1, then we see that this is slightly faster than in the case of phase rates I. This results in a significantly smaller number of phases if the coefficient of correlation becomes near to 1. So for 0.95 we need 75 instead of 105 phases. An additional effect is that the phase rates keep smaller, which might have an advantage in numerical analysis during the numerical analysis. We were not successful for negative correlation. The optimization problem in this case is slightly more complex, and the consecutive computation of weights does not work. The rates equal to I observe some local conditions for optimality, but they are not globally optimal. They are globally optimal for the case n equal to 2, but for n equal to 3, we've already found a better representation which, however, could not be computed from the representation with two phases. As an application example, we consider an MM1 queue where the inter-arrival and service times are correlated. This is an example for a sequential composition of phase-type distributions. In the left figure, we see the mean population for a queue with utilization 0.8. Depending on the coefficient of correlation, we see that the dependency is almost linear, and on the right figure we see the queuing behavior, and the difference between negative and positive correlation increases towards the tail of the queue. So there's a big difference for larger populations in the probability of finding a specific number of a specific population in the queue. Let me finally add that the results presented in this talk and several additional results can be found in a technical report which is available in arXiv and which will be updated from time to time, because there are several open points which hopefully can be solved in the future.